In this video, let's study the section 6.5, Properties of Logarithms. Well, logarithmic function is introduced as an inverse function about exponential functions. So it's not a very naturally defined function. It depends on another thing. So so far we didn't discuss a lot of special property or the basic property of a logarithmic function. We only know the domain range, increasing, decreasing part. Okay, so now let's check some basic and important property of a logarithmic function. The first one is that for whatever base, 1 has value always 0. The logarithm to the base a of 1 is always 0. When I put 1 here, it's always 0. The reason is that a to 0 is always 1. The exponential function with input 0 is always 1. So the logarithmic function with input 1 is always 0. And second, the logarithm to the base a of a is always 1. If you have the same base and the input is 1. It's also because a to 1 is a. Okay, so that's our two basic properties. Log a of 1 is 0. Log a of a is 1. Okay. And another thing, let's check here. B is log a of m. B is log a of m. So what does this mean? This means a to b is m. A to b is m, right? A to b is m. And well, b is this. This is equivalent. And b is written like this. So we replace this b by this expression. We get a to b is equal to m. Okay, so this is our second formula. What does this mean? Exponential function, logarithmic function, they are inverse pairs, so they cancel. Exponential, logarithmic, you cancel them, you have m is equal to m. See, exponential, logarithmic, you cancel two functions, you get m. And be careful, this m is positive. M is always positive. And another understanding is that the logarithmic function will give you the exponent. You put the exponent on the right position, of course you get the original m. Okay. And another thing is this, a to r is b. If a to r's power is equal to b, then by definition, log a of b is equal to r, right? So you try to compute the corresponding exponent to the for the number b. You choose the logarithm function to the same base, and b corresponds to r, and b is a to r. So you see here we do the same substitution. Log a to r, b is equal to a to r. You just do the substitution here. It's equal to r. And this also means you cancel the logarithmic function with the power function. They are inverse pairs. So you cancel them, you get r is equal to r. This r can be anything, any r. This m is only positive. This r can be whatever. You see? Just do substitution. substitution and you will cancel the terms. So keep these two in mind, it's very important. For example, if you have e to ln over 2, what's this? Exponential function, natural logarithmic function, they cancel, is equal to 2. Or you have log e to x, what's this? This is x. Logarithmic function, exponential function, they are cancelled, you only have x. But be careful, they have to have the same base. If they have different base, then you cannot do anything. And for example, let's do more. 2 to log 2 of pi, well, it's just pi, because here's base, they have the same base. And log 0.2, 0.2 to negative 2, it's just negative 2. Right? Okay. So that's our first two properties. First two. This one is not considered as property. This one is considered property 1 and property 2. It's considered as a calculation. Good. Let's see next. Next, we're going to show the logarithm to the base a of m times n is a logarithm to the base a of m plus logarithm to the base a of n. You have product, you will change it to the sum. The log of a product equals the sum of the logs. The log of a product equals the sum of the logs. The log of a product equals the sum of the logs. How? Why? Well, let's see. You have numbers. They are simpler than the log of the product. Let's call c the logarithm to the base a of m, and d the logarithm to the base a of n. We have those two numbers. C is a logarithm to the base a of m. It means a to c is m. D this, it means a to d is n. Okay, so we just apply the definition of the logarithmic function. Now, because here we need the product, let's do the product m times n. Now m times n is a to c times a to d. Exponential function has a property. A to c times a to d is a to c plus d. A to c plus d. So this number m times n corresponds to the exponent c plus d. So the log a m times n, log of the product, is equal to the c plus d. These two values have the product has a corresponding exponent c plus d. So you use a logarithmic function, you will get this exponent. What is c? C is here. Plus what is d? D is here. That's it. That is the formula we try to find. Okay, so you see here, that's this property. How do we get this property? We write it. We write those terms in terms of exponential function. We borrow the properties of exponential functions. The exponential function, you see here, the product of the exponential function is the exponential of the sum. It changes the product to the sum. Here it also changes the product to the sum. Right? You see, that's a property. And it's better for you to keep these two properties together. But this one is considered as a third properties of logarithm. Okay, next, let's see. We will start from this property. This property is very, very important. We know m over n times n, m over n times n, and log a of the product. Log a of the product is equal to log a of the first term plus log a of second term, right? From this property we have this. And m over n times n is m. So the left side is m. Let's simplify. And we move this term to the left side, we will get also, in most cases we write it in the opposite way. The log of the quotient equals the difference of the logs. The log of a quotient equals the difference of the logs. This is a fourth property. And this property is just a corollary of the second property. Okay, so these two properties are equivalent. Just choose a special product. Just choose a special product, you get it. Okay, so we have four properties already. Let's see next property. The log of a power is the product of power and the log. You move this exponent forward. How? How do we get it? We choose C. We use C to represent log A of am. Logarithm to A of m. Then by definition, A to C is m. A to C is m. Right? A to C is. And then we take r's power, because here is m to r. So we take r's power, so we get A to C to r's power. M to r's power is A to C to r's power. A to C to r's power is A to r times C. You get the product of those two exponents. Okay, so m to r corresponds to r to C. So the log A m to r is equal to r to C. It corresponds to this exponent. C is log to A of m. So it's r log sub A m. That's the formula. So the fifth formula. So you can see that we just manipulate the definition, and we transform them between the exponential and logarithmic function frequently. They are paired. You always consider them together. Okay? You always consider them together. All these properties can be done if you have the same base. If you have the same base. If you have different base, then there's nothing you can do. Okay? So let's check what we can say. A to x. Here, see here, m to r, a to x. This is a power. I consider the ln. Ln means we choose a special base e. then this is equal to x ln of a by the definition. Ln of a to x, m to r. You move x forward and you copy the ln of a. Okay, this is a property 5. This is property 5. This is a value. Consider this as one number. Ln of something is equal to it. Then by the definition of the logarithmic function, a to x is equal to e to x ln of a. Right? This base is e. You just move this e to the right side and write it as exponential function. So a to x is always equal to e to x times ln of a. And this is the property 6. Why we need this property 6? Because you see here, this base is arbitrary positive number a, not 1. Arbitrary positive number a. And after this transformation, you have the fixed base e. So we can rewrite whatever exponential function as exponential function with this fixed e. So we can unify the base. So that is the usage of this property. If you have different base, you cannot communicate between them. But by this formula, we can unify the base to the base e, and then you can do the computation. Right? So that's the idea of the last property. And that's possibly all the properties. There's one more property, but let's see if we need it or not. Okay, so now let's try to practice those properties. So we're going to write a logarithmic expression as a sum or difference or of logarithms. Okay, so for example, if we have log to the base a x times square root of x squared plus 1, we write it as a sum of logarithms. How do we do it? One thing, be careful about this expression. If you have a complex expression, it's better for you to use parentheses to clarify what is the input. Because if I write this, it will be very confused. I will be confused. What is input? You put it this way, then it means the log 8 of x times x. But if I put this way, it will be a lazy form of x squared. They are different. They are totally different. So when you have a very complex expression as an input, please use parentheses to make it clear. And also, if you have some coefficient, you will not put times 2 at the end if it's not inside. You will write 2 at the beginning to clear this is not inside the input. Okay, so that's a writing. Okay, now here let's try it. You have a product. Remember, we have the log of the product is the sum of the logs. And square root is power 1/2. So especially for this x squared plus 1 log, this term. If you write like this, I will consider this logarithmic function is only applied to x squared, not with 1. You must put parentheses to clear it. Okay? If you write this, I will consider you only take the logarithmic function to x squared, but you don't do it for the number 1. That's different meaning. Okay, and then this is the final thing. Logarithmic function cannot be distributed into the sum. Never. Sum difference, there's no distribution law. Logarithmic function works perfect with a product and a quotient, but not with a sum. Never with a sum. Okay? This one is a final stuff. There's no way to simplify it. Another. So if you have a log to the base 4 square root of x squared plus 1 over x cubed, x plus 1 to 4th power. Here x is positive, so we just assume positive x to simplify the discussion. Okay, so difference is not difference, quotient. Quotient is equal to the difference of our logs. Quotient is the difference. And then we separately discuss those two terms. The first one, square root, is a power 1/2. You move the power forward. Minus here is a product. Product, you are going to use a sum. And because you have a sum and this is a subtraction, put big parentheses. And then you have power. Here is the power. Okay, and then you remove the parentheses. You can remove in the last step. It's okay. So this is the final expression. And once again, log 4x plus 1, there's no way to simplify it. Okay? And we can separate or break a complex expression into small building blocks. We can also write a logarithmic expression as a single logarithm. So it means, let's see the examples. For example, we have a log a of 7 plus log a of 3. Once again, you have to have the same base. If you have different base, nothing you can do. So it is log by the sum is equal to the product. Sum of the log is the log of the product. So log to the base a, 7 times 3, 21. 7 times 3. B, 2/3 log 8 minus log 5 squared minus 1. Okay, so let's do it step by step. So it's log 8 to power 2/3 minus log 5 squared is 25. 25 minus 1 is 24. Okay, now let's understand this 8 to 2/3. This denominator 3 means you have a cube root. Numerator 2 means you have a power square. Cube root of 8 2 cubed is 8, so cube root of 8 is 2. 2 squared is 4. So this is log 4 minus log 24. So it's log 4 over 24. 4 over 24 is log 1 over 6. Okay, so this is to write a logarithmic expression as a single logarithm, and we simplify it. And I prefer you write the answer like this. In the book, they give you additional step. Log 1 over 6 is log 1 minus natural log of 6. Right? Natural log of 1 minus natural log 6 is the quotient. Log of quotient is difference of the logs. Log 1 is 0, so it's also equal to negative log 6, but I don't want you to do this way. You have to know how to do that, but I prefer the answers like this because we want to express it as a single logarithm. This one is a single logarithm with a coefficient. Okay. Next we have a log to a x plus log to a9 plus log to a x squared plus 1 minus log to a of 5. Okay. Whenever you see the sum, it will become the product. So you have an x9 x squared plus 1 as a product minus log to a of 5. Minus is a quotient, so it's log to the base a 9 over 5 x squared plus 1. It's the input, right? You divide the whole thing by 5, you just put it as a coefficient. Okay, so that is a properties of logarithmic function. The log product is sum of logs. Log quotient is difference logs. Log powers is a power times a log. Right? So that's all three properties. And then let's see. For the logarithm to the base a of n is equal to the logarithm to the base a of logarithm to the base a of m is equal to the logarithm to the base of a of n. Then it is equivalent to m is equal to n. Okay, so this is the theory which supports the solution of logarithmic equations. Logarithmic equations. So for example, what we have. We don't have, okay, so we will have the practice in the next sections, and the whole next section is about the solution of logarithmic and exponential equations. Okay, so we will leave the exercise in the next video, and then we have the idea. Okay, what is the idea? Idea is the following. See here, we want to find log 2 to 7, or possibly log 5 to 7, or possibly whatever number. So you choose a different base, you have some different value. You choose another base, you have another value. So this expression, it depends on the base. It also depends on the value. It's bad because we cannot have a big table. So what we do is the following. let y be log 2 to 7. The logarithm to the base 2 of 7. And then by the definition, 2 to y is equal to 7. Okay, 2 to y is equal to 7. And then we put natural log, you see here, you have an equality and then you put the logarithm. So here we put the natural log on two sides. We put the natural log on two sides. And the left side, we can apply the property for the powers. So we move y forward. And then we divide this equation by natural log of 2. Okay, so y can also be, y is a log to the base 2 of 7. Y is also equal to log, natural log of 7 over natural log of 2. But we like this formula better. Why? Because this formula, we have the fixed base e. When we have fixed base e, then we only need the evaluation of this natural log for whatever numbers, and then we put the quotient. Now we will get the answer. We don't have to get a huge table for logarithmic function with arbitrary base. Right? That is an application purpose. We like this this stuff. And this is called the change of base. You see here, originally it's e, now we change it to, originally it's 2, now we change it to the e. So it's a change of base formula. What is a change of base formula? Log a of m. You see, log 2 of 7. It is equal to what? It is equal to ln of, well, it's not necessary ln, it can be anything. So log b of m over log b of a. You can change the base to whatever, but be careful about this formula. Let me write it again. Log a m, and then you have log m and a. You can see m, a, they are in the numerator and denominator in the same relative right position, and you put whatever base b you like. You can put b equal to 1, not 1. You can put b equal to 2, 3, 4, e, 10, whatever. But this is a general formula. Usually we choose e, but this is a general formula. The general formula is called the change of base formula. Change of base formula. And the computation, the proof is like this. You write y, you take the you take the log for two sides, and eventually do the division. You will get it. Okay. Let me give you the proof. The proof is very quick. So let y be log am. Then by the definition, a to y is equal to m. A to y is equal to m. And then we compute the natural log to the base b. A to y is natural log, is logarithm to the base b of a to y is equal to the logarithm to the base b of m. And then we move y forward. Log ba, log bm. And you divide this equation by log ba. See? They equal to each other. So this is a proof. This is the proof. The change of base formula can be applied for whatever base you want this be. But in the practice, we prefer you choose the natural log as a base. You choose that e as the base of natural log. So this is a commonly used formula. It's a special case of a change of base formula. If you use the e as a base, or you use what? Remember the common logarithmic function. Use 10 as a base. If you don't see the base is 10. If you see ln, the base is e. Okay, so these two are the special cases, and the formula can be can contain whatever positive b as a base. Okay, so let's see the example. For example, if we have a log 589, it is equal to ln over 89 over ln of 5. If you have log to the base square root of 2 square root of 5, it is ln over square root of 5 over ln over square root of 2, and square root power 1/2. Square root power 1/2. So we get ln of 5 over ln of 2. ln of 5 over ln of 2. Okay, so that's a application of a change of base formula. So on page 456, there is a summary. The summary of properties of logarithms. Very, very, very important. You have to understand, you have to be able to apply them. Okay, do exercise. If you have question, send me email. Okay, we stop this video and we will start with a new video. Thank you.